All right, today we're going to pull back the curtain on two really powerful techniques that are pretty much shaping all of modern AI. We're going to explore the clever tricks that let these models get bigger and smarter without, needing a dedicated power plant just to run them. Let's get right into it.
For the longest time, the main rule in AI development, and this was really solidified by a big paper on scaling laws back in 2020, was incredibly simple. You wanted a more capable model, you just had to make it bigger. More data, more computing power, and critically, more parameters. And this chart really shows you just how wild that push for scale has been. I mean, we've gone from millions of parameters to billions, and now we're talking hundreds of billions. You have models like DeepSeek that are pushing well past 600 billion parameters, on their way to a trillion. The growth is it's absolutely exponential. Okay, so that brings up a huge question, right? If these models have a trillion parameters, does that mean every single time you ask it something, a trillion little calculations have to fire off? How on earth could we manage that kind of computational load? Well, it turns out there are some very, very clever answers. So, our first solution is a technique called mixture of experts, or you'll often see it as MOE. It's this really brilliant architectural trick that lets you build a massive model, but, and this is the key part, only use a tiny fraction of it at any given moment. It's all about working smarter, not just harder. So what exactly is a mixture of experts model? Well, imagine you've got a really complex problem. You could go hire one generalist who knows a little bit about everything, or you could build a team of specialists, an engineer, a lawyer, a doctor, and then only talk to the right expert for each specific part of the problem. MOE does that second one. It has a smart gating network that acts like a receptionist, sending each piece of information to the right specialist. And here's a fun fact for you. This new idea, it's not new at all. It actually dates way back to 1991, where it was first used for something super specific, recognizing vowels in speech. Kind of wild, right? It got a new lease on life at Google back in 2017, and now it's pretty much the secret sauce in a ton of the top models from places like Meta, Mistral, and DeepSeek. And this is where you really see the magic, the core reason this is so efficient. A traditional dense model. That's like forcing your entire company to attend every single meeting. It's just massively inefficient. But a sparse MOE model is like a good manager who knows to only invite the 2 or 3 relevant experts to the meeting, letting everyone else get on with their work. It saves a ton of time and energy. Okay, so here's a quick look at how it actually works. First, a little piece of data, we call it a token, comes into the MOE layer. Step 2, that gating network we talked about acts like a traffic cop. It looks at the token and says, okay, for you, I need expert number 3 and expert number 7. Then, in step 3, that token is sent only to those selected experts. The rest of the model, it just sits there, dormant, saving a massive amount of computation. Now that's MOE, but it's only half the story. Let's move on to our second solution, which is called knowledge distillation. This one tackles the scaling problem from a totally different angle. If MOE is about building a bigger model more efficiently, distillation is about how you can shrink a really big model down without it losing all its wisdom. The concept here is it's really beautiful and intuitive. You've got this massive, super powerful teacher model. It's way too big and slow to actually use in a product, but man, is it smart. So what you do is you use that huge model to train a smaller, much more nimble student model. The student literally learns to imitate the teacher, capturing all that intelligence in a much more compact, efficient package.
But how does the student learn so effectively? Well, the secret is something with a really cool name, dark knowledge. See, the teacher doesn't just give the student the single correct answer. Nope, it shares its entire thought process, all the probabilities, the nuances, the maybes.
Let's break that down. A hard label is super blunt. It just says, this picture is a cat, 100%. But a soft label from our teacher model, that's a whole different ballgame. It says, look, I'm about 85% sure this is a cat, but it has some dog-like features, so there's maybe a 10% chance it's a dog. And it's a little sly, so maybe a 5% chance it's a fox. This teaches the student all the subtle relationships between concepts, which is what makes it so much smarter. What this does is pretty brilliant. It completely separates the training process from the inference process. That's the part where we actually use the model. Think of it like a butterfly. During training, the model is like this huge, complex caterpillar, just consuming enormous resources to learn everything it can. But for deployment, it transforms into a small, fast, efficient butterfly. We get the best of both worlds, massive intelligence during the learning phase and nimble speed when we actually need to use it.
So we have these two incredible tools in our toolbox: mixture of experts to build these giant models and knowledge distillation to then shrink them down. Now for the really cool part. Let's see how the world's top AI labs are combining them into this powerful 1-2 punch.
This table right here? This is basically the playbook for modern AI. First, a company like Meta or Google will build an absolutely enormous teacher model, often using a mixture of experts architecture just to make it manageable. Then, they use that monster of a model to distill all of its knowledge down into a whole family of smaller student models. And those are the ones they often release to the public. So, what's the big picture here? Why do these two techniques matter so much for where AI is headed? Let's bring it all home. The most important thing to remember is that MoE and knowledge distillation aren't just some abstract academic ideas. They are the core engineering solutions that are making today's AI explosion possible. They let us balance this relentless push for more and more powerful models with the very real-world constraints of cost, computation, and speed. They're the reason we have incredibly powerful models that can actually run on our devices, and not just in a handful of giant supercomputing centers. And that brings us to a final thought I want to leave you with. These techniques are, without a doubt, ingenious solutions to the scaling problems we face today. But in the ridiculously fast-moving world of AI, as soon as you solve one bottleneck, you usually just reveal the next one waiting down the line. So the question is, have we really solved the scaling dilemma? Or is a brand new challenge waiting for us just around the corner?